sure I was late today, but now I see it's 10:10 right on the mark, folks. We're getting started. Well, you have hopefully had a chance to get in and look at the Virtual Ecology site, kind of browsed around, poked in and out, saw different things up there. Did anybody have trouble getting onto it? Just let me know, because I did find a couple of folks who did. I gave them the link, they tried to step into it, and it totally fell on their face. Now, that first person was a computer specialist, and he finally said, actually, I have a little bit of a blockage on some things. Maybe that was it. I'm like, oh, okay. But now I know everybody else got in fine. Hopefully you've spent your time there, and you know that where we're going on Friday is to pick up that entrance into the Forestland site. And when we do that little trek, we're going to be looking at the different trees on the two different permanent plots. We're going to measure every tree, and we're going to enter it into the Excel file. Now, that Excel file is available for you on the Canvas site. You go down to the modules for this week, and you'll find that after today, that there are two Excel file, or one Excel file I needed to download. There's a couple of PDFs as well, but what we're going to do on Friday is enter those tree data into that Excel file and begin the processing of it. Now, that processing chart, though, that's what we're doing today. I want you to know a lot about this whole idea of how we do forest land sampling at this very survey level class. Okay, in other words, we're SOE 300. You're going to go into other classes, especially if you're in forestry specifically, where you do that stratified random sampling. You're going to be looking at the different needs of the sampling you do. That sampling idea is totally to be able to look at a population and say, I can't measure every single individual. I don't want to. I don't need to. How about I do a sample of them and use that sample to make statements about what the whole population looks like? And that's what I'm going to define and discuss right here. You see a couple images on the screen right now of the two permanent plots that we're going to visit and use in this class this week. Now, these are the plots we're going to go and visit physically next week. Now, a little tiny side bit on that is I got to say I timed class perfectly to have this beautiful weather all week for our virtual class while we're indoors. And then next week when it starts to rain and gets super cold. So we're going to do it. Just dress warm. I'm going to have my hat, my warm coat and boots. That's fine. We're going to make it work, but be ready for it. It's going to be cold too. We'll do the field trips. It'll be fun. But now what I'm going to do is walk through this whole thing about the Virtual Ecology site and begin to just kind of pause up in your head. Why do you do sampling at all? Yes, Nick. They're on Canvas for today's lecture. You'll find the PDF in that link. This slideshow is available right there, right now, for today. So you can download it and follow along with it and take the notes all you can. That's totally the preparation. Now, this is one of the videos, or yeah, one of the shows that is not a video, at least not yet. It's the presentation I have today. And oh, a sideline on that, and Nick, thanks for asking that, because our class on Monday, I pulled that off of Zoom. I fixed the audio, I trimmed it, and I put it up on the site. Now, last Monday, or a couple days ago, that was Aiden Almel sitting on the screen and giving the rundown of how to use this Virtual Ecology site. I've replaced it this morning. I did put it up to YouTube, and it's now available. It's listed, it's unlisted as a video, which means if you got the link, it works fine. It's available for you right now. You can log in, watch that. So if you had a question about Monday, how to use the site, there it is. You can see exactly what Monday's lecture was. It's right there on the Canvas site right now. So with this idea about looking at the different populations and what we're visiting, what we're understanding, why do I do this random sampling at all? Well, the whole idea of the random sampling is that we're going to not bias our selection. I want to describe the population, but you got to ask the question, what kind of population are you looking at? What kind of information do you really want to glean from it? Now, in forestry, as this basis level of a sample, I want to know about the trees that are growing out there. What is their size, their species, their age? What is their distribution? How many trees am I talking about? Can I describe those trees? How am I going to describe trees? Well, I'm talking about diameter of breast height. That's a common measurement that we all make. In forestry, we'll go out there and we'll measure it right at 4.5 feet above the ground. That's my DBH. And I also want to know how tall that tree is. I need to know the species. Okay, now all those different descriptions, I'm starting to put out the net of what kind of things I need to know tree by tree to make population description events. And that's what we're going to walk through here. Well, that's for the overstory trees. Hey, we also want to know, what is the understory vegetation? That tells me a lot about the animals that will use it as a feeding source. Now, tell me a lot about who's living there beyond just the trees. These are the kind of things I want to know. This is what I need to describe so that other folks who are coming into the site get a good picture of it without having to physically visit it or go and watch a bunch of videos. No, I just want to see the results. Tell me what it is, describe it. This is what we're going to step into here. Let's see if I can get this overhead bouncer to normally to go away. No, live on Twitter. There we go. So we're doing the statistical analysis. Now, a lot of folks will have already had a stats class. That statistics class you take here, if you're in any of the natural sciences, it is an obligatory class. You need to take it. You need to understand what kind of data you collect, how you analyze it, and then basically how you present it as well. It is really this step into the idea that you're not going to bias your samples. Okay, we keep going through this, but one of the key phrases, two of them we're going to step into today, is stratified random sampling, and then the other is a variable radius plot. That stratified random sampling is really a basis for how we do all the different types of sampling in natural resources. It doesn't matter if I'm dealing with salmon spawning or salmon rearing. How about the different fishes, the birds, the deer, the elk, the moose, all these different critters? That's for the wildlife side, and for the trees. When I get into that stratified random sampling, literally what I'm doing is looking at a population, let's say a forested area. You'll hear me use that term a lot, the woodland type. Okay, a woodland type, that's very generic, very broad. If I talked about Kamiak Butte, I could say, yeah, I have a population of trees out there. You know, is it just the trees? No, it's the habitat where they live. So I'm looking at all that land, the 560 acres of Kamiak Butte. Okay, that's pretty broad. And you know already that the north-facing aspect and the south-facing aspect have two different, very different populations on them. Right there, I just introduced the idea of the need for stratified random sampling. Within a stratum, I'm going to say this stratum of trees, it is one characteristic that they're very uniform within that stratum, very different from the next stratum over, the adjacent population. So I have the north-facing aspect, that may be one stratification I make. The south-facing aspect is the other. I just separated the population into two groups. That stratification means that I'm going to just sample the north-facing aspect separately from the south. Then as I take that group of species and the data that I find, I'm going to be able to describe it. I'm describing something very specific on the north-facing aspect for the Douglas fir, western larch, ponderosa pine. Also, if I reach far enough, I'm going to get a little bit of grand fir as well. Well, that little pitch around to say that grand fir, hold on a second, that's a big changeover, because the plot we're doing today, we're going to walk through the examples of on Friday, it only has Douglas fir, western larch, and ponderosa pine, not a grand fir on it anywhere. Okay, right there, that means my stratification has more variation than just that north-facing aspect. That grand fir exists on the far western side of the butte. Now, on the virtual ecology site, you will have seen that whole discussion about the grand fir that grows out there. There's a short video clip I made about identifying the grand fir and how it has that wonderful sniffy smell. Okay, but these are the kinds of stratifications you might start to look at and say, yeah, we can re-stratify and make a finer definition of it. Today, we're not going to do that. Instead, I'm going to just walk through this idea of the SRS, the stratified random sampling, to say that is one way that we sample, is very useful if we use it right. Okay, then we're going to make statistical comparisons between these different groups. That whole side of statistics, where you're going to have different ways of describing, of course, the average. We got the mean. We've talked already about that with the PRISM data, right? We picked out those ideas of how we're going to use that mean and min and max. How about the standard deviation? The variation within those numbers gives me a feed for how specific or how broad they are. These are all the things that we will pick up a lot about when we're doing the analysis or data processing of everything we have. Let's see if I can get back to my keyboard here. There we go. So with this random sampling, what I really want to have is every time I make a stratum, I want to have the difference between my groups maximized. But then within the strata itself, very specific. As much as I can keep those strata very unique in that respect, that means my statistical analysis data, what I process and what I present on it, it's going to be very specific. It's really going to work for you. But for this, right now, we're just going to know that this is a part of that random sampling idea. We are going to really divide the populations out. Just knowing that's what we've got, where we're taking it out, how you're going to decide where your lines are made. Now, I've already told you one little lead in here is that we have some grand fir on the north-facing aspect of Kamiak Butte, but we don't have it in any of our samples. Knowing that that is a definition of flag that flies up right away to say, maybe I need to have another strata introduced. And literally I would put that marker, now we'll talk about it when we see the graphs on the screen, but a marker to say this is a new strata that we want to identify. There we have Douglas fir, ponderosa pine, western larch, and grand fir. Okay, all of a sudden we now have the 4 species, and really we may lose that western larch component when we do that. Again, another maximization of the differences between the strata. These are just the steps you're going to want to take, and just know this is where we go. So on this whole idea, different definitions and terms we use, some of the measurements we're going to make. One of them is what I already mentioned a little bit, is that diameter at breast height, 4.5 feet above the ground on the uphill side of the tree. Now, you know up at Kamiak Butte, when we get there, you'll see it. You're either going up or you're going down. The only flat spots anywhere on the butte, they put a pavement down and said, this is a parking lot. Everywhere else, we're climbing or dropping. That's all right. When you get in the forest, you're going to find that tree. You're going to put a plot center into the ground. For me, I would always take a flag and jab it in the ground. That flag in the ground, I have to number it and put my initials on it, but that was plot number 2. Okay, I just got a number. Now, that is my plot center. For the process of doing the sampling, then, pull out the compass out of my vest pocket and turn up to due north. I would turn my stance right over the center of the plot, and I'd run the compass at perfectly due north. That became the marker of where I would start my sampling. From that point, I rotate clockwise. Do a little spin around and identify every tree that I'm going to measure. So as I go around, I see the Douglas fir, another Douglas fir. Oh, there's a grand fir. Here's a western larch, a ponderosa pine. I'm just doing that circle and running on my notes what those species are. At the distance, I can do them easy. You are going to get to where you can identify them fine. You got your short abbreviations like we're going to use in class is a 2-letter abbreviations for the common names. Douglas fir, DF. Western larch, WL. Ponderosa pine, PP. Okay, those are just the markers that I'll make. Then from there, I leave the plot center, and for this stratified random sampling, whether it's with a clinometer, where there I'm using the diameter at an angle from that plot center and making a spin, and it becomes a plot proportional to the size of the tree, the PPS. That plot proportional to the size is telling me if it's a big enough tree with the angle that I'm using, it becomes an in tree or an out tree. And that'll determine how many trees I'm going to measure. Typically with the PPS, I don't want more than 7, but I have to use the same angle on every single plot I do within that stratum. Don't change it between them. It's always the same one. So I may be out on this side with a 20 BAF, basal area factor. That 20 BAF angle that I use it on all the plots I do of that woodland type. Now out here, we're doing something a little bit different, and it's called this variable radius plot. Okay, this variable radius plot literally says the same idea. I put the plot center in the ground, and then I measure to the trees within my zone. I want to get between 4 and 8 trees on every sample. Okay, and that sample, again, I want to be consistent with them, but every plot now has changed. So literally I put that plot center in and I measure the distance to all these trees until I have that 4 to 8 trees identified. And maybe 4 to 7, 4 to 8 in that range. The very first time I stepped out here at Kamiak Butte and did the initial plot settings, I measured a little bit long. I think I got about 27 trees within the fixed plot. That's way overkill. So I ratcheted it back. Now we have this, well, you'll see it, but it's 7 trees on this plot that we measure. We're within that range. But now what I have to do is measure the distance from the plot center to the tree itself. We'll step on that one a little bit more, but really, what data am I going to collect? I'm going to collect that distance from plot center. I'm going to collect the tree species, its diameter, breast height, and its total height. Okay, those measurements are going to give me the definition and the description of the tree that I have, or the trees that I have out here on the plot. And with those data, I'm going to be able to make assertions about the entire population. That's what we're going to do, and that's how we're going to really send this thing through. Okay, and that is me on the plot, by the way. Actually, that's the very first permanent plot, and this is the one we're going to visit physically next week when we go up to the butte. But this is what we're going to see virtually on Friday as we go through it as well. So this whole plot radius thing, if I were to come out here and say that tree number 6, for instance, is 17 feet away from the plot center. Okay, now I have that marker. That's telling me a lot about the distribution and density of the trees. You got to think about that. If I have a whole population of trees around me and I want to measure 4 to 7 trees on this plot, what is the distance to the furthest tree out in my selection? Okay, I just have a good identifier. And if I am using, for instance, tree number 6, I say it's 17 foot away. Okay, that means I at least have that kind of a distribution available, but I want to make it more. I want to be able to say how many trees per acre does that represent? Well, a sample of 1, it doesn't tell me anything. I need the entire sample processed and identified, and we'll kind of walk through this and do exactly that today. We're trying to capture a lot about this mix, this difference, the biodiversity that the site represents. That's why I'm recording all these other data as well. I'm picking up the species, that height, the diameter. What are the characteristics of these trees that I want to identify? This radius, that 48 tally trees, that's what we call them, the tallies. On some plots, I'm going to land out there and I won't have more than 5. I'd have to go out there 50, 60, maybe 80 feet to get that 7th tree, just because they're so distributed well. They're broadly distributed. I don't have a lot of trees. Literally what happens when I step on the south-facing aspect. A lot of those plots are barren. I can see a tree way over there. I can see one down here. But really, it's not heavily populated as it compares to the north-facing aspect. And these are just the steps that we're going to go through. But really, what we use for these in or out trees, I have it's called a Spencer tape. It's a tape that rides on my hip all the time. It is self-retracting. It goes out 100 feet. I have a horseshoe nail in the end of it. I put it in the bark and I walk away. Now I have that distance that I needed. Literally, it's walking back from the tree and measuring to the plot center. That's my distance from plot center. Hey, but where do I measure it? Is it the face of the tree that I saw when I measured it? Nope. Is it all around the tree itself and then stretching out? No. You want to go to the edge of the tree that's perpendicular to you. I got to get the edge of that tree as I see it standing there. In this scenario, if this is the tree, I'm going to hit it on the right-hand side or the left-hand side, right in that center area. That is the distance from plot center, is the center of the tree, not the face of the tree. Okay, a little tidbit for you, just be able to use it when you can. But now those become my in and out trees. And obviously on the first measurement, it's just identifying what is the distance from plot center. And I hit this one already with that 4.5 feet above the ground. That uphill, downhill thing, on the very first plot that we're going to visit on the field trip at Kamiak Butte, we're going to see that that very first tree is on a steep hill. And if I stand on the downhill side of it, literally I'm only about, on the uphill side, about 1 foot off the ground. To be able to get that distance up at 4.5 feet on this side, stand on the uphill side of the tree, and there is where you measure from that ground uphill level side up to 4.5 feet. That's why I'm going to use the DBH. Now, I know you probably have all been through it by about 8th grade when you're doing geometry class, that you know about the circumference of a circle. You know about pi r squared, right? That whole wonderful thing. Well, we are so lazy in forestry that we have diameter tapes that show distance on one side. I flip it over, and right there is diameter. I wrap that around the tree, and it'll give me exactly what the diameter is to 1/10 of an inch. That's the wrap around the tree, and it gives me that whole feed through to say, this is exactly what I have. So that is what we'll do that out on the site, by the way. I'll bring a couple D tapes. Everybody can touch them and use them if you want. But that is kind of the routine that we use. Okay, on these written plot records, everything that I'm going to record, I talked about this already. One of the big ones, though, that I talked about on that compass that I take as a shot to the north, and I spin clockwise. Okay, that spin now, as I get those in trees, I number them. 1, 2, 3, 4, right around the edge. Those become very specific because I want to be able to make sure that anybody who does a test plot to check my measurements, they're going to be able to find exactly the tree that I found when I made that first measurement. It's super important, and I did this in retrospect, way too many years. That was a remote field sampling where I was out doing these timber stand exams. I'd be out for maybe 10 days straight, camping out, living in the camper or in a tent. But we were very remote doing these samples. And then the client had to come out and do test samples as well. Make sure that we were really giving good data, accurate data. They're paying for it. It's money, right? So they got to come out and do these test samples. Great. They could land in any of my plots they selected at random and find right there a spin of that site and know the tree number 3 was right there. Yeah, he's got it numbered. It's that Douglas fir. It is that height, that diameter. They test those things out. Okay, that is part of making sure your data is good, but also knowing that you're going to be able to work with other people when you do this. Whether it's a test cruiser that comes out to check your work, or maybe a colleague who's working on the information that you collected, and then the assertions you made about the site that you saw. Okay, all these different data, all these information, these are the things we are going to measure right here. But then you got to take it to the next step. You're going to analyze those data, and literally we're going to do that on Friday. We're going to be looking at specifically the first plot in great detail, opening the door for you to do plot number 2. But now what you're going to have to do is, how are you going to use those data to describe what you're looking at here? Well, for instance, I can say, well, I'm on the north facing or the crest area of Kamiak Butte, looking to the south. This is on the south facing aspect of Kamiak Butte, and literally in the distance, as I go up to the very farthest reach of that photograph, I'm looking in the direction of Pullman right now. That's exactly where we're sitting. But now I got to describe those trees. Obviously, I've got the ponderosa pine. I've got a diameter of about 24.5 inches. I've got some understory vegetation, which is mainly elk sedge grass. Okay, and that's just looking at the photograph. I see a bunch of downed trees. Yeah, start to ask yourself, why do those trees lay down? They get tired? What's going on with this? Why are those trees down? What killed them? Why didn't they burn up? We talk about fire-adaphic species, those species that respond to the wildfires that occur out here at Kamiak Butte. Important number for you. The average fire return interval at Kamiak Butte before the advent of humans coming in and mucking it up was about 12 years. Every 12 years, we had a wildfire come through Kamiak Butte. Now, I want you to think about that number right away. That 12 years, would you think that that was a barn-burning fire? Was it a hot, baking fire that just annihilated everything? Nope, it ain't. It's a low-intensity fire, especially in this grassland area, where that was a low-intensity surface fire that it burned and scarred some trees, but it didn't kill them all. Obviously, there's a few trees dead right there, and so it killed some. And those trees, when they died, they were still standing because you see that there's a lot of biomass left on that rascal. It just died. And then eventually it fell over. There it is lying down. There are some bigger fires that happen, not just every 12 years of low intensity, because it didn't burn 100% of the land either. It burned in spots and patches across the butte. Sometimes it was controlled naturally. Sometimes humans jumped in and did it. And it's not just the settlers that came in after the 1700s. No, the Indians did it too. The Native Americans were out there. They were doing prescribed burning of their own. They did their own wildfire control. That just isn't the same way we do it, where we're pitching people out of perfectly good working helicopters to parachute to the ground. Okay, that was always a crazy thing for me. I never jumped out of a helicopter voluntarily, never. But I did a lot of wildfire fighting and saw how we can control a lot of this disturbance matrix we look at. Anyway, you're looking across all this. How are you going to describe it? What are you going to do? This is going to come back to something I tapped into a little bit earlier, as I'm looking at that tree out there. Now, I've just virtually taken the top off. Imagine that's a live, living tree. And I talk about describing that average DBH. I want to say, what is the average diameter breast height of the trees that I'm sampling within this population type? I talk about that, where you have a ruler, you hold that ruler out, and you see, I got a straight measurement there. This is the diameter of the tree. I got to say, that isn't a way that I can average. What I'm really looking at on this tree is that circumference right there. That's flat area. It's really a quadratic area. This is a diameter that is expressed as a circle. This is the thing that I got to do the averaging of to say, if I have all the different trees of different diameters, that a 10-inch tree versus a 12-inch tree is a vast amount of difference when you're looking at the surface area of that 12-inch cut. That is why I'm dealing with this whole idea of basal area. This is a much better definition and description of the size of the trees and how many trees does it take to make an average difference if you're on a straight line versus that quadratic area. Okay, it's quite a bit different, and what you become available to say is when I do this quadratic mean diameter, I'm giving a much higher accuracy and descriptive ability of those data. This is how you want to describe it, and it doesn't matter if you're just doing it for this class today or if you're doing this in anything in forestry. As you start to describe these things, know that that quadratic mean diameter is a very valuable and useful metric for you to know how to come about it, how to use it, how to do it. I'm going to take it right back to the formulas here, and I got the BA as basal area. I'm going to say, I want to describe the basal area per tree. I'm going to say that's going to equal pi times dBH over 24 squared. Now, in this case, that dBH, you know it already, diameter of breast height in inches and tenths of inches. I'm going to take everything down to about 1/10 of an inch because that is what I can measure at. When I go out to the plot with my D-tape, I put it around, I've got down to 1/10 of an inch. I don't have hundreds or thousands. I don't need it. But down to the 1/10 of an inch, that's just fine. Now you see that 24, it is another scalar constant that you're going to see because we're dealing with inches here. 12 inches per foot. Now we're using the 24 here. This is just our modifier for that dBH. Now let's put some hair on this and start to give some examples now. I'm going to take that basal area per tree. I'm also going to be able to turn it into a basal area per plot. So I'm going to do it per tree and then combine them together within that one plot to say, now, what is my basal area per plot? I'm going to be able to reach out and say, what is my quadratic mean diameter of all the trees that I sampled on this one plot? Now, that is a little bit of processing ideas that you need to really comprehend, grab it in good. We're going to do the calculations in Excel, like I say, on Friday, but it's all set up for you to understand right now. How do we go step by step? Because I can do it per tree, per plot, and then I'm going to take it up to the per acre side. How many trees per acre do we have on this woodland type of each species? And then be able to describe what did they look like, those average trees. What does the average Douglas fir on Kamiak Butte on the north-facing aspect look like? Give it the diameter, its quadratic mean diameter, its average height. Okay, all these steps around, that's what we're going to walk through these one by one. So this basal area per tree, I gave you that formula already. Now let's start to put some numbers in. In this case, I'm going to say that this tree number 4, I just grabbed one of the trees off of our list. I'm going to say this one, 33.14, that's pi. You can take that pi out as far as you want. We talk about significant digits a lot. Hey, on this case, I will be a total admit on this. I always use pi as a saved in my calculator, as a saved in Excel. How many ever digits it takes, that isn't my significant digit worry. I'll take it out as far as it'll go, and then use it with my significant digits on my 1/10 of an inch diameter. I won't trim this one back for pi or for any of those other constants like this. But okay, we push those numbers through. Remember your order of operations. You're first going to take the 21.4 divided by 24 and then square that, and then multiply by 3.14. Always that order of operations. Start in the parentheses and work your way out. Okay, when I get them all fleshed out, I come up with this number as the basal area of that tree number 4. In this case, was about 2.49. Okay, that is the number that you want to calculate. This is what you want to use as part of the calculation process. Step by step. That was tree number 4. Also notice how I subtitled that calculation. I put the subtitle 4. Okay, that just tells me that's tree number 4. And let's keep pushing this along now. If I want to take this out to the per acre area, I'm going to start with that basal area per tree. We've already got that calculated. Now I'm going to do that for every single tree on the plot. Got to run each one of them through, making sure your data is good all the way up, and then do the calculations to get that basal area individually per plot, per tree on each plot. Then to get that out to the per acre level, I'm going to take that basal area per plot, which is just the sum of the basal areas per tree, sum them all together, and then I'm going to multiply it by this trees per acre. Now on that TPA side, you keep that one running around to say the trees per acre. How am I going to come up with this? I need to know how many acres I'm dealing with. There's a PDF on the Canvas site right now for this class today, where you're going to be able to click on that, and it's going to show a woodland area map of north-facing aspect and south-facing aspect with acres attached to it. So I've gone from the plot, where I did that sample, the variable radius plot. I know the distance to the farthest out tree. That's going to allow me to say that is an area statement about this one sample plot. Now I'm going to take those data and I'm going to extend it all the way up to this entire woodland type if I know the number of acres. I know the square foot area of that plot I have because the furthest out tree. I can now extrapolate that to expand it all the way up to the entire woodland type. Those numbers are out there. Let's see how we can use them off of this. You know now the area of a circle. I'm taking it back to 8th grade geometry, right? Okay, that is, in this case, area is equal to pi r squared. The pi, we know, the r, the radius, that variable radius plot we made. Okay, that's going to tell us a lot about our plot sample, but now I'm going to throw another variable in there, that 43,560. That is the number of square feet in 1 acre. Okay, that number of square feet is going to give us that link around to say, this is my extension or magnification factor. If I know I'm dealing with 10 acres, I'm going to multiply that 43,560 by 10. Now I've got the total area of the site that I'm looking at. If I know the area of my plot, great. Now I have the ability to make the linkage from one to the next. And pull that 43,560 around and say, now I'm just going to modify that pi r squared formula. What if I divided both sides of that pi r squared equals 43,560, divided it by pi? Okay, the right side, pi divided by pi, cancel out, they're gone. It's r squared is equal to 43,560 divided by pi. Okay, I know pi is a constant. I know 43,560 is a constant. So now I can just pop those rascals through and say, I'm going to unsquare that r squared, take the square root of both sides, get the radical of that 43,560 divided by pi. Again, do it inside of the fractor first, and then come out to your number. A little fast there, Dr. Bill. There we go. And we got the 117.78. That's a perfect circular radius of an acre. Conceptually, this lives only in the classroom. You know, we're talking about a round circle here because we had pi up there, and I can make a circle exactly of that radius, 117 foot. I've got a perfect acre. We never make it, right? What do? We make rectangles and squares on the ground. That's all right. This gives us our first step around to say, I got to make the linkage from one to the next. We've already been here. You saw that area of feet in an acre. But now for our variable radius plot, let's spin this around the opposite direction. Where are we going? I'm going to say that trees per plot, and I already know what it is because I counted how many trees I was able to capture within that variable radius plot distance, measuring to the farthest out tree. Don't let that one trip you up, by the way, folks. You'll be asked different questions about this as we go through, and folks will stop to think about that farthest distance out. So when I had 23 trees, I could have just given everybody that same set of data and say, now here is a sea of 28 trees. What is the variable radius plot you would use? What would you do? You put them in order of distance away and choose from the closest to the 7th out tree. Now that's not my new distance. That's a new variable radius plot. So literally, I've already trimmed off those other 20 trees, left 7 of them just for you. That's now what you're going to use. You're going to put it through this whole same formula process to say, what am I coming up with? My trees per acre? Well, if I know that I had 7 trees on my variable radius plot, I know my radius. Oh, radius squared. Now this is back to that distance you measured from that plot center out to that tree, that farthest out tree. If I measured 27.3 feet out, that was the furthest out tree. Now I have this ability to translate my one plot up to an entire woodland type. So in this case, that 43,560 divided by pi times 27.3 squared. Okay, step by step, I can really walk that rascal through and come up to say, I now have a proof of my measurement to come up with 130 trees per acre. That's a big step around for you now. You just went from that one variable radius plot using these data, using those easy and quick formulas to say, now I'm going to be able to extend this out to say on the entire woodland type, I've got about 130 trees per acre. That's all in together. All of the species on this type. It doesn't tell me anything about how many Douglas fir, how many western larch, how many ponderosa pine. But I know that there's a difference between them because I have different counts of those species too. But this is how we make that linkage from one to the next. Great. So we've been here. We've done that calculation. We know now the basal area per tree. How am I going to calculate that? I'm going to plug the numbers in. I know what they are. I can plug them through and say, in this case, as I do my order of operations to see them step by step, I'm coming out to a basal area per tree of 1.65, which really tells you nothing, right? Nobody's sitting around saying 1.65 basal area, oh, big, oh, small. Now, for height, we know about that. When I talk about the diameter, when I turn that quadratic mean diameter back into a physical measurement that I'm familiar with, then I can say, yeah, that's this certain kind of tree. This is that description that I can take around. And when I describe it, you'll know it. Be able to step on them, but let's keep a hold of that 1.65 and say, I got to work that one back through the toothpaste tube. I got to find out what was the diameter at breast height so that I can make that mental comparison across all of these. Let's keep on moving it then and say, I'm going to keep that 1.65. You got it there. With that basal area per acre now, I'm going to take that trees per acre times the basal area per tree. This is that average number that I came up with. So I apply these across. Now I can say with 130 trees, I come up with the total basal area per acre. Again, at arm's length number that says this is just the basal area that has no meaning to it. I'm not talking about temperature. I'm not giving you a foot of deep a depth of snow in feet, right? You got a conceptual realization on that, but we're going to use that 214 and use it to work backwards, understand really where it means for describing this woodland type. So this basal area per acre then, as I keep going through, I'm going to push that trees per acre and the trees per plot. Step by step, you see it here. It's at the very bottom, the trees per acre, trees per plot. Again, back to the same numbers. Trying to pull out that average tree diameter is what I'm walking you through here to see how I'm going to go to make the entire summary and then pull it back down to numbers of meaning. Keep walking them around. You see the same numbers. It is just pushing the calculations around. The basal area per plot, I'm using the summation of them. Bring it back to divided by trees per plot times that, one more magic number, that 43,560 I told you. It's a number you're just going to know if you're working in any form of natural resource management and doing any type of analyses. I don't care if you're forestry, wildlife, geology, anything else, you know 43,560 is a constant. You're just always going to remember as an acre. Now here, this 005454, it is another conversion factor. When we're talking about acres, you're talking about diameter and pi. Okay, that is a constant, that 0.00545415. Okay, those are the numbers that we use as a conversion. It doesn't matter what area of sampling you're in, if you're dealing with acres. In the United States, yeah, that's our number. We got to tap it and just know that is a constant that we're going to use just like it's pi, but it's not pi. It's a different number. You see the full pushed out variable here, 0.00545415. That's the constant we're going to use. For calculating this quadratic mean diameter then, it's literally a central tendency, which is considered more appropriate than just taking the arithmetic average of the numbers. Now, when I talk about height, I'm totally good with that. You got 105 foot, 104 foot, you got another one over here at 110, and you calculate that average and you say that's 106 foot. Okay, conceptually, I can do it just like that. But when I come up to diameter, this is where the quadratic mean diameter is more appropriate for it. What you're going to find is a difference if you try both of them. Just do them side by side. Do it on this plot set that we're doing now. When we do it on Friday, you're going to be able to do a simple average and a quadratic mean diameter. Do them and see what the differences are. See and justify in your head why one is smaller than the other. Always smaller than the other. Understand why that is the case. Why was your sample biased because of that? Well, as I push through these numbers now, I'm going to look at that whole formula for the QMD as the radical of the sum of the basal area per plot divided by that trees per plot times that 0.00545415. Okay, all these variables around, great. I can push them up and say that's my quadratic mean diameter. I'm going to be able to calculate it and just know that I come up with a number that has a meaning. So on this case, my example, average basal area per tree is 0.16504,625 square feet. Okay, again, that is that arbitrary number, not arbitrary. That is that number that has no measure stratification on it. I don't know, is that square feet? Is that inches? Is that distance or depth? You don't know. It's a variable that has multiple factors involved in it. We're going to use that to come up with our diameter in inches. Okay, in this case, we take that formula again, the base fill area per tree, that 1.65, divided by our magic constant, and it comes up to 17.4. Now I have a measurement that means something. You notice I put the inches on the end of that little double hash mark. Okay, that tells me that this tree represents 17.4-inch quadratic mean diameter. That is the diameter that means something to me and to you. You can look at that tree and say, wow, 17.4. Now, the next number is, I got to look how tall this is. On the north-facing aspect, I'm looking at something around 110 feet. I'm going to weight it to say this quadratic mean diameter tree, it's an average, has an average height of this species of this much. Now I'm getting that description. This is really where I want you to take it. I want you to know it. Every step you do it, it's going to come out to the outcomes. How your equations are going to calculate things, and then you're going to describe it. So what you're going to do for this class, you're going to calculate those two plots. We'll walk through it very detailed on Friday for plot number 1. You're going to do number 2 on your own. You're going to verify a bunch of things out of number 1, and those will be your tree data. You're going to submit that Excel file that you create in class into the Canvas site. That'll be the assignment attached to this. But then for the term report section, you got to describe them. This is where you're going to write about it. You're going to say and describe these 2 different stratified random samples of Kamiak Butte. Describe what you see out there. I'm doing it with a lot of calculations here for the trees and what the descriptions you're going to make are. You're going to use those. You're going to write about that. You're also going to tap into some things about the understory vegetation, a little bit about the geology. How much exposed rock? Is this all vegetated? Is this all dry? Is this all grassy? Is there exposed rock? Okay, all these different things that you can see as you describe this woodland type. This is how you're going to do it, folks. This is where you're going to take it, where you're going to describe literally to make it a point of your own. Just some pondering questions for you to really consider out here, and answer the questions partially to yourself and partially in your term report section. What species are more abundant and why? Why do I have a whole bunch of Douglas fir and western larch and ponderosa pine on the north-facing aspect? But really, when I land on the south-facing aspect for where we have the sample, I only have ponderosa pine. Now we're going to look up there on the actual field trip and walk around and see a few Douglas fir on that south-facing aspect. Those unique microsites, it's going to be another question for you to consider. Why? Why here do we have a Douglas fir, but we don't have any western larch? I have 0 grand fir out there. Why? Okay, those are part of the forest succession ideas and the topics when we talk about how the different species are adapted to the environments where they live. Okay, all these different questions you can walk around. Why are some trees bigger? Like the ponderosa pine. Here's a great question. I'll even preempt it for you. When we get to the ponderosa pine on the south-facing aspect, you're going to find their diameters, their quadratic mean diameters, are pretty big. They are very comparable to anything you'd find on the north-facing aspect too. You got a 24-inch tree on the north-facing and a 24-inch tree on the south. Well, they're equivalent trees, right? Until you look at their heights. What if I tell you that on that north-facing aspect, it's a 110-foot tall tree, 24-inch diameter? Get on to the south-facing aspect. Here's a 24-inch diameter tree. It's 30-foot tall. That's a little tiny stumped-off tree. That's like the carrot I pulled out of the garden. It was really tilted at a sharp angle. It's because of the different ability of the tree to grow on those sites. We talked a lot about the photosynthetically active radiation in class. This is a place where you start to identify and really just consider why. These are your proofs of the pudding here. How are you going to walk through the limiting factors? That's one of them, but now describe it more about the available moisture, about how the plants are able to thrive on each site. There's also a big spin around on this, and I will say that in the past, I had another task that I really put everybody to say, and the initially is about carbon sequestration of, carbon on Kamiak Butte. Going into each species, and literally there's a video that I want you to watch before coming to class on Friday. It was the field trip of this class in the spring of 2020. Okay, that literally was the very ending of the in-class live classes as the pandemic hit. That on the Friday, the last day of our classes on WSU, we did the field trip. We took samples from the forest. Those are increment bore samples. We drilled into the trees. We pulled out a core sample and we put them into plastic containers. We brought them back to WSU. Here we put them into a dehydrator. That dehydrator over at Steffen Center, right here on campus, dried out the moisture from those tree samples. We then put them into mass spectrometry. Now, mass spectrometry is another unit that is available right here at WSU through the ARS. Agricultural Research Service has offices here, and Jenny is the manager of that site now, but she did all the sampling with us. The TAs were in the lab, watched how that machinery works. We made a video of it. That is what the TAs and I did in the spring of 2020. Now, here we are 2 years later, and I'm not having to do those field samples this time. Hopefully, again, we get back into it, but right now you can watch that video and understand how that mass spectrometry works. It's telling me what is the content of carbon in those tree samples, species by species. I'll tell you straight up that as an average, I'll just bark it out this way to say, as an average, trees are 50% by weight carbon. So I talked about that whole carbon sequestration that the trees do through photosynthesis. They pull out the oxygen from the CO2 and throw it away for us mammals, and they keep the carbon to grow. That carbon is half the weight of the tree. It's a board. Whenever you put it up in your house or in your table, you use that board, half of that is carbon. We just sequestered a lot of carbon, and it all came from the atmosphere. But remember that one, folks. I told you, all the carbon dioxide comes out of the atmosphere. All the carbon the trees use, they can't take a stitch of it from the ground. It all has to come through photosynthesis. Enabled because they took nitrogen out of the ground. Even though we have 72% nitrogen in the atmosphere, again, they can't sniff up any of it. They got to pull that out of the ground. Now that board, that weight of the carbon, that is the measurement that we have here. One of the challenge I threw out to everybody, and I gave bonus points for it. The first semester, I said, everybody do it. After that, I said, no, now everybody, if you want to do it, I'll give you bonus points. At this point, I pulled it back. I said, I'm not going to throw it out for anybody again, because last semester and the semester before, I think I got one student a semester who did it. And by the way, those students did not need the bonus points. They were already at 120%. They did not need more, but they did more. So for all of you, if you're interested in it, I'd walk you through it. Absolutely, I'd share it. We would do a meeting right here in class or after class where I'd share how those data are how we come about those data and process them. There's a lot of mathematics again, but just keep this one in your mind. Those trees are sequestering carbon all the time. They're putting it into the wood stalks, all the woody materials of that tree. It's the tree bole, it is the bark, it is the branches and the roots. Don't forget about those roots, because that is carbon. Once sequestered, it's going to stay down there. Even if it burns down up above, that carbon is released up to the atmosphere again. It's converted. It's a conversion process of fire that puts it back into the atmosphere, generally as smoke and carbon dioxide. But in the roots, that is more carbon that is sequestered that is going to just rot and remain in the soils, because the plants, they can't bring it up out of there. Only some microbes, right? They can decompose it and respirate and put the carbon back up that way. That's another thimble measurement of how much carbon comes out of the ground because of those rotting roots. But for now, just keep this one an idea that this is a part of the process we walk on, what we step through, and how we do it. With all of that said, folks, we've got a lot of conceptual ideas that I've shared with you today. What I'd like you to do, go back to that Canvas site, grab the Excel file, pull a copy of it to your local machine. You're going to fill that out on Friday with me. We're going to step through it here. You're going to finish it and turn it in class. You'll turn it in on Canvas after the fact. But literally, folks, if you do it here in class, you'll be done with that assignment and put up to the site. I'm giving bonus points if you do the full calculation of quadratic mean diameter for all the tree species, for all the plot. You're going to get that summation of all of them. And what I've done is you got to do that. That quadratic mean diameter, we just spent the entire 50 minutes on this. But when you push this up to your assignment and then use it in the term report, you got to have that quadratic mean diameter. So I just sweetened the deal. You're going to do the 100-point assignment. And when you do it all with the quadratic mean diameter too, you're going to get 125 points for it just by doing what you're asked to do as the original segment. So you're going to get a bonus just by doing the work. writing about it now, that is even more. Take that one up to the highest level, make a great term report section out of it. I'm going to spend a little bit more time on it on Friday to talk about what goes into that term report section, that next one in the line. Going to be able to hit this nicely, folks. Got to take a deep breath now. We went through a lot of good stuff there. Have a great rest of the day. Spend some more time in that virtual ecology site. Anybody who wants to get over to Chris Lavore and get the Oculus headsets on, this is totally a great time to do it.
Thank you.
Have a good day.